Here we are taking another look at the chain rule, and we're going to do some more examples. So the chain rule is what we use when we are differentiating a composite function, a function that is created by the composition of two functions, f of x and g of x. And so if we compose g of x into f of x, g of x is our inner function. Talked a lot about this on the first video. G of x is our inner function and f of x is our outer function. And so identifying that from the beginning is what we're going to want to do, and then we can apply the chain rule. And the chain rule essentially, we are looking at their rates of change and multiplying the rates of change. The rate of change of the outer function times the rate of change of the inner function. So in Leibniz notation, dy dx is dy du, derivative of y with respect to u times the derivative of u with respect to x, and that's the outer derivative times the inner derivative. Now, when we do take the derivative of the outer function, we are evaluating it at g of x, or what we call u. We also do define g of x as u. And so here's our other version. We can just say the derivative of that composition is f prime of g of x times g prime of x. And so I wrote these down here, and I want to get into, we did several examples on the first video, but I want to get into some examples where we actually combine some of our other rules. So notice here that we actually have a product. So when I come across this, I think first, oh, I'm going to use product rule. But notice that each of these functions is actually a composition. It's a polynomial composed into a power function. And so when I apply, I have to actually sort of peel away all the layers as I take this derivative. So when I'm taking the derivative, I have to apply the product rule because this is a product of two functions. Then when I take the derivative of each of those two functions, I have to apply the chain rule. So that's the thought process here is, you know, I've got a product, so I have to apply the product rule and the chain rule as I'm applying the product rule. So that's what I'm thinking as I'm looking at this. And then I can get in here and actually start doing it. So we've had some practice with the product rule, so let's get going working with the product rule. So we're going to use the product rule. I'm actually going to erase my little thought bubble here. Actually, maybe I'll just move it over a little. All right. So as we're taking this, when we take f prime of x, remembering from the product rule that I have to take the derivative of the first function. So I'll write it all out. I'm going to take the derivative of 3x squared plus 4 to the fifth, and then I have to multiply by the second function, my g of x in the definition of the product rule, x cubed minus 2x plus 1 to the third. Then I'm going to have to take the derivative of the second function, x cubed minus 2x plus 1 to the third. And it looks like I did not move my thought bubble. Derivative of the second function times the first function, 3x squared plus 4 to the fifth. And then as I'm doing each of these derivatives, I notice that I have to actually apply the chain rule. So for each of these derivatives, I'm going to be applying the chain rule. And so as I apply the chain rule, I have to think about what's my interior function and what's my outer function. So what's my inner function? What's my outer function? So my outer function here is, on this first one, my outer function is the actual power function, the quantity being raised to the fifth power. So as I take that derivative, I take the derivative of the outer function first, evaluated at the inner function, which would be 5 times that quantity to the fourth. That's my power rule. But I'm evaluating it at 3x squared plus 4. Then I have to take the derivative of the inner function, 3x squared plus 4. And I'm going to write that step out. Most of the time we're going to skip to this next line. So I'll write the next line at the same time. But I want you to see that we're taking the derivative of that inner function to get to this next multiplication here. So the derivative of 3x squared plus 4 is just 6x. Okay. Then we are multiplying from the product rule, x cubed minus 2x plus 1 to the third. So that will come down. All right. and then to the second half of my product rule. So same thing here. I have to apply the chain rule because I have a composition. I have to identify what's my inner function, what's my outer function. My outer function in this case is, again, a power rule, and my inner function is that polynomial. So doing my outer function, so we're going to have the derivative of the outer function is, again, application of the power rule. So we have 3 times that quantity to the second power. The quantity, what I'm evaluating it at, is that inner function, that g of x cubed minus 2x plus 1. Then I have to multiply by the derivative of that inner function, the rate of change of that inner function. X cubed minus 2x plus 1. And from the product rule, 3x squared plus 4 to the 5th. Now, like I said, most of the time I'm trying to show all the steps here so we can see it all. Let's get it all on the screen so that we can see it all. But most of the time what I'm going to do is I'm going to go ahead and take those derivatives as I'm going and show my work here on this next line. So the derivative here, so taking this derivative, right, that just like we did on that last line, taking this derivative, I get 3x squared minus 2. And then I'm multiplying by 3x squared plus 4 to the 5th. Okay, and now I have quite a long expression, or quite a long function, long derivative. And what I want to do is I want to see if there's anything that could be simplified here. And so as I'm looking at this, I'm thinking, is there any common factors that I could pull out? And I do see quite a bit of common factors, right? I've got this polynomial in both of these two terms. I have this polynomial in both of these two terms to some power. I can pull out, actually I can pull out x cubed minus 2x plus 1 to the second, and I can pull out x squared plus 4 to the 4th. Let's see, what else could we do? Maybe a 3 actually. There's a common factor of a 3. I could pull out a 3 from here. Okay, so I'm looking for my common factor here, and I'm seeing a common factor of 3 times x cubed minus 2x plus 1 to the second, and 3x squared plus 4 to the 4th. And so I can pull that common factor out from both of those terms in this function. So let's go ahead and do that. So we'll put that in the front. That'll clean it up a little bit. And we do want to do that. We don't want to leave a long, messy, unsimplified function. So we'll pull all that out, and let's see what we'd be left behind with. So if I take out the 3 here, the 6x is going to become a 2x times 5, so we'd have a 10x there. And one of those x cubes minus 2x plus 1 is going to be left behind. And then we're going to pull the 3 that's out. We're going to have a, none of the x cubes minus 2x plus 1s are left. We pulled all of those out, but we have a 3x squared minus 2, and one of these 3x squared plus 4s left behind. Okay. All right, and then of course we would want to continue to simplify, distribute now, and see where we end up here. So this becomes 10x to the 4th minus 20x squared plus 10x plus 9x to the 4th plus 12x squared minus 6x squared minus 8. And let's just go to the next line for our simplification. So we have 3x cubed minus 2x plus 1 squared times 3x squared plus 4 to the 4th times 19x to the 4th let's see here, that's a 6x squared minus 14x squared plus 10x minus 8. And there is there's my derivative using the chain rule in the midst of the product rule. See if we make that a little bit bigger there on the last screen. All right, let's take a look at another one. So here we have a function that is clearly a quotient. So we've got our f over g here. So we'll have to remember quotient rule to apply this, to take this derivative. We'll have to apply the quotient rule to take this derivative, remembering that this is going to be f prime times g minus g prime times f over g squared. Now, when I do that, though, notice that each of these, both the numerator and the denominator, are compositions. We've got functions composed into other functions. So when I take the derivative of the numerator, I'm going to have to apply the chain rule because it's clear that this has an inner function of 5x squared minus 1 composed into an exponential. And in the bottom, we have this little linear function, 3x plus 2, that has been composed inside of a root. So this is the inner function here. So we're definitely going to have to break this apart as we go through taking derivatives, taking the derivative of the large quotient, and when we take derivatives of the numerator and denominator, we're going to have to apply a chain rule. So we're layering upon layers, right? We're taking all of our rules, all of the tools that we're building up here now, and using them in problems in multiple, using multiple tools in one problem, multiple rules for taking derivatives in one problem. Okay, so let's go ahead and get at it. I'm going to go ahead and I'm going to erase some of my notations. Well, we'll leave the notations and we'll just get going at it. So let's take the derivative. So if we want to take this derivative, so if we want dy dx, remembering that we first have to apply that quotient rule. So I'm going to go ahead and write in the operators, and then when we apply the chain rule, we'll drop the chain rule to take these derivatives, we'll drop the operators. So if I'm going to take the derivative, the quotient rule says I have to first take the derivative of the numerator. So we're going to need to take the derivative of e to the 5x squared minus 1. Then I'm going to multiply by the denominator, and the denominator is the square root of 3x plus 2. Then I'm going to subtract the derivative. Now I'm not going to take the derivatives yet, I'm just going to write in the operators. Then I'm going to take the derivative of the denominator. Now, because this is the same as writing 3x plus 2 to the 1/2. That's how I'm going to write it in here. And, in fact, let's go ahead and write it right here too. Let's just write that as 3x squared. This will kind of simplify our notation here. Let's just write that as 3x plus 2 to the 1/2. Instead of using roots, let's use those rational exponents. So this will be 3x plus 2 to the 1/2. So when I take the derivative, I can apply that power rule to that derivative within the chain rule. And then we need to multiply by the numerator. So oops, too much popping up here. So the numerator here, e to the 5x squared minus 1. And this is all going to be over the denominator, 3x plus 2 to the 1/2, or the square root of 3x plus 2 squared. Okay? So that was our application of right there. When we took that derivative, because it was a quotient, we had to apply the quotient rule. So there's our application of that. Now we haven't taken the derivatives yet, so now I'm going to get in and I'm going to take the derivatives. So the derivative of the numerator, because it is a composition, I have to apply the chain rule. And so when I do that, I take the derivative of the outer function. The outer function is the exponential, and the derivative of an exponential is just itself. So when I take this derivative, and I'm going to go ahead and do just the derivatives in red so we can see that. So this is going to be, when I take that derivative, it is going to be e to the 5x squared minus 1. It is the exponential evaluated at the inner function. So we keep the inner function. We took a derivative. I know it doesn't look like we took a derivative, but we did. It looks the same as e to the 5x squared minus 1 because the derivative of e to the x is e to the x. Now here's the part where we're applying the chain rule. We're also taking the derivative of that inner function. So we're going to take the derivative of 5x squared. That is just 10x. Now I carry down the rest of it, 3x plus 2 to the 1/2 minus, now we're going to do the same thing when we take the derivative of that 3x plus 2 to the 1/2. We have to apply the chain rule, and the chain rule says, let's do this in red as well, where the chain rule says that we take the derivative of the outer function, which is the root or the 1/2 power. So we take the derivative by applying the power rule, 1/2 and then subtract 1, so this becomes to the minus 1/2. Now we're keeping the 3x plus 2 because we're taking the derivative of the outer function and evaluating that derivative at the inner function. Then I have to multiply by the derivative of the inner function. Well, here is the inner function. So the inner function is the 3x plus 2. So we're working on this derivative right now. So the inner function is 3x plus 2. So the derivative of 3x plus 2 is just 3. And then I carry down the e to the 5x squared minus 1 from the quotient rule. That was our f. All over, and in the denominator, of course, we have 3x plus 2. When I have the 1/2 power, which is a square root, and I squared, of course, those two cancel out, or you could use rules of exponents and just multiply. 1/2 times 2 is 1. But that becomes just 3x plus 2 to the first power. Okay. Now we're going to get in here and we're going to simplify this thing. And, when I'm looking at this in terms of simplification, I'm thinking to myself, you know what, let's pull out in the numerator. As I look at the numerator, I think, when you think about simplifications and you're thinking about what to pull out for your common factor, and we do want to pull out a common factor, what I would suggest is that you look at, let's see if we can get it all on the screen so I don't run off the screen as I write my common factor. You're looking at, okay, of course we're going to pull out an e to the 5x squared minus 1. That's one common factor. I see this 1/2, and I don't really like having fractions in fractions, so why don't we also pull out a 1/2? So we'll pull out a 1/2 e to the 5x squared minus 1. Let's see, do we have anything else? We've definitely got that 3x squared, or just 3x plus 2. Let's pull out the minus 1/2, the smaller of the exponents. So we'll pull that out to the minus 1/2. So let's pull that common factor out. I'm going to put that down below. Actually, it's making it too small to write. So let's put that right there, and then I can zoom in a little. Okay, so that's what we're going to pull out from each of the terms in the numerator, and let's see where that leaves me. So pulling that out, if I put a 1/2 e to the 5x squared minus 1 times 3x plus 2, and that'll be nice because I can drop that minus 1/2 power to the denominator and add it to the power that is already down there. Let's see what we have left behind. So if I pull that out, I'm obviously going to have a 20x because we're pulling out a 1/2. So when you divide by 1/2, you're multiplying by 2. So we've got a 20x left behind. The e to the x is gone, but we do have a 3x plus 2 to the first power because we're taking out that minus 1/2. So 1/2 minus a minus 1/2, add, and that becomes 1. Over here, the 1/2 is gone, that's gone, and that's gone. So all that we have left here is a minus 3. And we're still dividing by the denominator, 3x plus 2. Remember that that is to the first. So I am going to drop this guy, this minus 1/2 power. I'm going to drop that down. When I do that, I'll be adding 1/2 to that 1. And we will also go ahead and distribute here. So in the numerator here, we're going to end up with 60x squared plus 40x minus 3. And I'm going to also drop the 1/2. I'm going to pull that down as well. Drop the 2 to the bottom. So we have e to the 5x squared minus 1 times all that's left in the numerator, 60x squared plus 40x minus 3, divided by, now we've dropped the 2 and the 3x plus 2 now to the 3 halves. And that is a nice simplification, right? I've spent a lot of time on these videos going through some simplification because it's prepping us for some future work with these. Or, if I were to simply have said here, like find where this has horizontal tangent lines, or find what the tangent line is at x equals 0, or whatever it might be, right? We could now plug in those values for x, or we could set this equal to 0. This does allow us to having these simplifications does allow us to work with these derivatives in a more mathematically easy way, right? Like instead of having to do the simplification When we're doing other applications with the derivatives, we've already got the derivative simplified. And if we practice it as we're building up these tools, we'll get better and better at this simplification. So here is the whole picture. So it was a quotient, so of course we had to apply the quotient rule, but within the quotient rule, we were applying the chain rule on this example. Before we move on to our next example, I just wanted to mention that those last two examples that we did utilized some generalizations that we could put together. We could say that the power rule combined with the chain rule, if we have a function to a power, that is a composition, but if we think of it specifically as a power rule, that we've composed a function into a power function, then this rule is sort of our generalization. We could utilize this generalization. So if we have a function to a power, then our derivative is going to be n times that function to the n minus 1 times the derivative of that function. And there's the Leibniz notation down there too. And similarly, if we have an exponential function and we've composed a function g of x into that exponential function, so we've got a function in the exponent of an exponential function, then the derivative is going to be, if the base is e, then the derivative is going to be e to the g of x times g prime of x. And if the base is anything other than e, a, then we have that, remember, we have that natural log of a constant that pops out too. So, this basically allows us to, while they are still chain rules, this allows us to take, let's just do two quick ones. Like if we were to have 3x squared minus 7 to the 11th, say. If I were to take that derivative, that really is just g of x to the 11th, to the nth power. And so when I see that, I think, okay, I'm going to take the derivative. The outer function is the power rule. And so that's 11 times 3x squared minus 7 to the 10th power times the derivative of the inside function, the g of x, which is 6x. And so that gives me, and we could kind of quickly go through that when we have a function raised to a power, remembering that it's chain rule. So when we take the derivative, we take the derivative of the power function times the derivative of the inner function that was composed inside. And in a similar way, like if we were to have g of x equals, let's do that same function, 3x squared minus 7. So if I have 5 to the 3x squared minus 7, or even if I had e to the x, let's move that over a little bit. Let's do both 5 to the x and e to the 3x squared minus 7. With the generalization here, when I take g prime of x, that's going to be, again, I see that exponential, so I think, okay, this is going to be, and the base is not, notice here the base is not e, it's 5, so I will have natural log of 5 times 5 to the 3x squared minus 7 times the derivative of 3x squared minus 7, which is 6x. And so we could rewrite that. We've got that constant natural log of 5, and I don't want to simplify that. I want to leave that in its exact form, times 6x times 5 to the 3x squared minus 7. Okay? And when I say simplify, it would have to actually be an approximation. And so I don't want to approximate the natural log of 5. I want to leave it just like that. And in a similar way, h prime of x, if the exponential itself is the natural exponential is the base, then the derivative is simply e to the 3x squared minus 7 times the derivative of that function that we composed into that exponential, which is just 6x. And so kind of remembering that we've got that power rule and that exponential rule, we have created some generalizations that we could state, and if you want to write these down, they definitely are useful. They really are just applications of the chain rule. We're just applying the chain rule when it shows up in a power function. We're applying the chain rule when it shows up in an exponential function, but they do create these generalizations that occur. All right, so let's get back to looking at another example, an example that has some layers to it, some complexity to it. And so let's take a look at this one. If we have g of x equals the tangent of the sine of x squared minus 1. This is a composition. We've actually composed, this is a composition of three functions. We've composed x squared into the sine of x, and then we've composed that function into the tangent of x. So there are layers here. There are definite layers of composition. So there are multiple compositions here. There are multiple layers of compositions here. And so let's think for a second to our chain rule. And our chain rule says, you know, if f of x is equal to f of g of x, that as we peel away the layers, as we take the derivatives, as we look at the rates of change, we take f prime of g of x times g prime of x. So what happens then if our function is, rather than just a composition of, let's not say or, let's say what about a composition of more than just two functions? What if it's, you know, layers of functions? What if we have h of x composed into g of x composed into f of x, right? So we've got 1, 2, 3, like the one we're looking at, like the particular example we're looking at. How do I deal with that? Well, I have to peel away the layers. So the derivative is going to be f prime. We take the derivative of the outermost function first, evaluated at the inner function. Then we have to take the derivative of the inner function, but the inner function is a composition. So I have to take the derivative of the outermost function within the inner function. It's kind of a tongue twister. So I have to take g prime of h of x. Then I have to take the derivative of that inner function, h prime of x. So I have to go through all of the layers. You know, what I say sometimes is it's like peeling away the layers, like an onion. So we're peeling away the layers, okay? And working our way to the innermost function, to find the innermost rate of change. So we work with the rate of change of the outermost function, evaluated at the inner functions. Then we work with the, then we multiply by the derivative, the rate of change of the next inner function, and then we work our way all the way down in. And so we end up with, this kind of like layered chain rule, right, as we go down. And so when we look at this one, that's exactly what I'm going to do. I'm going to say, well, what's the outermost function? Well, the outermost function is the tangent, and so I'm going to take that derivative first. So as I go through here and I work my way through these layers, I'm going to say, okay, so the derivative is going to be equal to the derivative of the tangent of x first. So the derivative of the tangent is secant squared. So it's going to be secant squared of the inner function. Well, the inner function is sine of x squared minus 1. Then I have to multiply by the derivative of that inner function. But that inner function itself is a composition, and so I work my way through that. So the derivative of the sine of x. So I take the derivative of the sine of x first. The derivative of the sine of x is the cosine, but I'm going to evaluate it at x squared minus 1. And then I finally get in, and now I'm taking the derivative of the innermost function, and I multiply by 2x. So we have our multiple layers there. There is not much I can do to simplify that. So we'll just, because we've got compositions within that product, right? And so we're not going to be able to simplify much. You certainly can't multiply into a composition there. So we've really just got the product of those three functions there, and we'll leave it as that. So remember, when you have multiple layers like that you just work your way through. Let's, I think it's worth doing one more example right here on this one. I wasn't going to, but let's just do this one. What if we had something like e to the sine of 3x, right? It's a little subtle, but there really is a composition of three functions here. You've got 3x is your innermost function. It has been composed into the sine of x, and then the sine of 3x has been composed into an exponential. So as we work our way through this, as we take this derivative, and I'll go ahead and use Leibniz notation here, dy dx, we have to start with that outermost function, which is the exponential. So the exponential, the derivative of e to anything, is e, and it's going to be e to the sine of 3x. Then I have to multiply by the derivative of the sine, which is the cosine of 3x. Then I have to multiply by the derivative of the 3x, the innermost function, which is 3. So we really do. We just work our way through peeling away the layers, right? Think of it like an onion. You're peeling away the layers as you go in. Again, there's not a whole lot to simplify here, but I guess we might as well write 3e to the sine of 3x times the cosine of 3x. We could just move the constant to the front. Okay. And there's our derivative. Okay. Okay, let's just do one last example on this video before we end it out. Okay, so let's wrap up here with this one. Find the equation, and actually since I added one, this is technically our 5th example on this video. So let's find the equation of the tangent line to this curve, y equals the cosine squared of x plus, that's a new trig function there with a funky backwards s, cosine of 2x at x equals pi over 4. And so here on this one, the first thing, obviously, when we've done this so much now, but the first thing we need once we're finding either a slope of a tangent line or an equation of a tangent line is we got to find the derivative. So let's find dy dx. So let's get right in there, take our derivative. Now, this particular function is cosine of x. Now, we do mathematically put the square right here where we're seeing it in the notation, but that really is a composition, right? It's the cosine of x composed into a square. So it's the cosine of x squared plus this is also a composition, cosine of 2x. And so we are going to have to apply the chain rule twice here as we take this derivative. So we'll want to just be careful of noticing that when you've got a trig function squared, even though, it's written like we have here that I have highlighted, even though it's written like that, remembering that that really is the cosine of x being composed into a square function. So the outer function is that power function, the inner function is the cosine. So dy dx, the derivative of that first term, cosine squared, is going to be 2 times the cosine of x to the first power times negative sine of x. So, peeling away the layers there, right? There's the derivative of the outer times the derivative of the inner. Plus, then we're going to take the derivative again. This time the inner function is the 2x. Okay, so the derivative, we'll take the derivative of the cosine, the outer function first. So that's going to be minus the sine evaluated at the inner function 2x times the derivative of that inner function 2x, which is just 2. Okay. So the individual derivatives themselves are not difficult there, but we do want to just make sure that we apply that chain rule appropriately. And so this derivative, if that's all I was looking for, could be simplified into minus 2, let's see, sine of x, cosine of x, minus 2 sine of 2x. Okay? All right, so we got our derivative. Now we need to actually find the equation of the tangent line. So to find the equation of the tangent line, we need a point. So let's actually find equation of tangent line now. So we know that x equals pi over 4. So let's find the ordered pair. We've got the derivative. We'll find the slope second. Let's find the ordered pair. So to find the ordered pair, let's plug pi over 4 into our function. So we know we got pi over 4. Let's figure out what is that ordered pair. What would y be if we plugged in pi over 4? So the cosine squared of pi over 4 plus the cosine of 2 times pi over 4 is going to be, well, the cosine of pi over 4 is root 2 over 2, and we're squaring that. And then the cosine of, 2 times pi over 4 is the cosine of pi over 2, so that's actually 0. And so the y value here would be, let's see, 2 over 4 or 1/2. Okay, so we've got the ordered pair 1/2. So there's our point, and now we just need a slope. Okay, so the slope, so dy dx at x equals pi over 4 for our slope. Slope of the tangent line, that's going to give me the slope of the tangent line. I'm going to put that actually on this side. That's going to give me the slope of the tangent. And that's going to be equal to, let's plug in pi over 4 right up here. So minus 2 times the sine of pi over 4 times the cosine of pi over 4 minus 2 times the sine of 2 times pi over 4. 2 times pi over 4, by the way, is just pi over 2. So I'm going to write that in, pi over 2. And so we get minus 2 times root 2 over 2. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. Minus 2 times the sine of pi over 2 is 1.
And so what we're going to end up with here is minus 2 times 2 over 4 minus 2. What do we get there? Minus 1 minus 2, and my slope is a negative 3. So we've got our point and our slope. Let's put it all together now. Okay, so putting all that together, and y minus 1/2 equals negative 3 times x minus pi over 4. Y minus 1/2, distribute negative 3x plus 3 pi over 4. Add the 1/2, and y would be equal to a negative 3x plus 3 pi plus 2 over 4. I also found a common denominator while I was, so add 1/2 and add 1/2, and then made that 2 over 4 so that I could add it. And here is my final answer. And we do want to write our answers like this, leave them in their exact form. Let's not go to an approximation. Let's leave it right like that. So get a little bit of that earlier example on the bottom of the screen here, but there is the whole problem right there. So finding that equation, applying that chain rule to both terms in that function, because cosine squared is the same as quantity cosine squared. So I have to apply the chain rule to peel that apart, cosine of 2x, and then following it all the way through, find that slope of the tangent line and the point and the equation of the tangent line. Okay, so those are some really good examples of all of our rules, really, as now we've added in the chain rule.